We welcome you once again to this very interesting series of talks that started a couple of years back in the name of Kaapi during quarantine. And we earnestly hope that this will be the last talk in this series, and we will go back to our Kaapi with Kuriosity very soon, where we would have offline programs here at the planetarium, and we see people in person, and this quarantine period would be over once and for all. So with that hope, I have the pleasure of welcoming you once again to this KDK series of talks organized by ICTS. And on behalf of ICTS and Jawaharlal Nehru Planetarium, I welcome you all who have joined us online. You have been extremely supportive of this program all through this pandemic, and we hope that your support will continue in the same vein when we switch over to the offline mode, where we have more of personal interaction with the speakers, which is always very charming. So first of all, we would like to welcome Professor Mahuya Datta from Statistics and Mathematics Unit. She's from Indian Statistical Institute, Kolkata. And the topic is really very interesting, something that cuts across all disciplines of sciences. So people are not just mathematicians who will be interested in this tilings, people who do crystallography and then a whole lot of physics, chemistry, and biology are interested in this topic. Therefore, I hope that the heterogeneous audience that we get will have something to take back home from this topic through this presentation. And so with that very short introduction and strongly hoping that next time we will be meeting offline, I now request Professor Mahuya Datta to begin her presentation on tilings. Now over to Professor Datta.
I would like to introduce Professor Datta. So hearty welcome everyone to KDK. Today's speaker is Professor Mahuya Datta from Indian Statistical Institute, Kolkata. She did her undergraduate studies at Presidency College, Calcutta, and then did her master's degree from University of Calcutta. Thereafter, she joined ISI Kolkata and worked with Professor Amiyo Mukherjee for her PhD thesis. She did her postdoctoral study at International Center for Theoretical Physics, Trieste. She joined Kolkata University as a faculty in 1996 and then moved to ISI Kolkata in 2003. Since then, she has been working there. Her broad interest is in differential geometry, and most of her research work can be classified under the theory of H principle, which deals with partial differential relations in differential geometry and topology. So today she has picked up a beautiful topic, tilings, and we are really looking forward to it, Mahuya. And you can post your questions in the chat box and it will be answered towards the end. If you have something very urgent to ask, you can unmute yourself or raise your hand and it will be taken care of. So over to you, Mahuya.
Yeah, thank you. Thank you, Rukmini, for the introduction. Also the invitation to the KDK series of talks. And so thinking that this is a very wide audience, I have chosen a topic which is called tilings, which we are all familiar with because we see tilings around us every day. So be it the floor of the room or whether we walk on the pathways, you always see tilings. So here we will discuss the mathematics behind it. To start with, it will be very simple, which will be accessible to the high school students. And then you will see some glimpses of geometry, how tilings can be extended from flat surfaces to curved surfaces, and where the geometry has to play a role. And then if time permits, we'll also relate this tiling with group theory. So this is the more or less the outline. So this is the content of the talk. We have a very brief section for preliminaries where we discuss the basic concepts. We will not do it very rigorously, but mostly rely on our intuitive ideas of tilings. Then we study Euclidean tilings as well as Archimedean tilings on the Euclidean plane. Then we'll generalize these concepts to spheres, which are curved surfaces, and we'll see some more geometric relation with this. So what is a tiling? It's not a very rigorous definition, but I think most of people will agree with this. This is a very informal way to say a tiling is a covering of a flat surface by some non-overlapping shapes, leaving no gaps. So you are given some pieces and you have to cover a surface in such a way that there is no gap left and no two pieces overlap each other. Generally, the flat surface is the infinite plane R2, but you can also have some subsets of R2 as well. So the tiling that you see in this picture is made up of two types of pieces. One is the pentagon, as you can see. This is a pentagon here. And then there is another, this is a rhombus. So we have used two types of tilings to cover the entire plane R2. So each of these pieces will be called a tile. So this is a tile. Similarly, this is also a tile. So any particular shape that has been used will be called tile. The picture that we see here are certain these tiles are in the shape of a polygons. That means this is the convex hull of certain number of points, but it can be also different. So the tiles may also have curved surfaces. For example, here, these two sides are curved, these two sides are straight line segments. But here in this particular talk, we will be we'll be only talking about tiles which will have edges. This is the boundary part. This boundary will consist of finite number of straight line segments. So let us look at the following thing. These are all examples of polygons. This is triangle, this is square, this is a regular hexagon. So all these examples are given here are of course polygons, but they are convex. This is the first thing, convex polygons, because there may be concave type of shapes. This is not allowed. So these kind of things are not allowed. On the other hand, these are regular. So what do I mean by regular? So a regular polygon means that all its sides must have same length and all angles must be congruent. So these are, so you must be familiar with regular convex polygons. So this is a equilateral triangle, this is a square, and this is a regular hexagon. Now, if you look at any of these shapes, this boundary made up of a few straight line segments. This will be called edge. So this is called edge. And if we look at two edges which are meeting at a point, so this is called a vertex. So these are some of the definitions that we will be using. So given a tile, we look at the boundary. So boundary consists of certain straight line segments which are called edges, and if two edges meet in a point, then that point is called a vertex. So this is an example of a H2H dialing. So what do I mean by H2H dialing? If you look at two adjacent tiles, then you can see that they meet along certain edge completely. So if you look at this edge, this is common to the octagon as well as this is common to this square. So this is a common edge. So two adjacent tiles are meeting at a common edge. If you look at the if you look at this picture of tiling, then you will see this is not an example of a H2H dialing, because this is the edge here, and whereas the other edge is this. So they are not completely meeting along the edge. So these kind of tilings we will not consider. We will only consider tilings that meet along the edge completely. So these are called H2H tilings. What we are interested in is a H2H dialing, and where the tiles are in the shape of a regular convex polygons. So what is a regular tiling of a plane? So you are given the complete R2, that means the Euclidean plane, and this will be any regular tiling. By regular tiling, we will mean that it is an H2H dialing, and whose tiles are only of one type, and that one type is a shape of a regular convex polygon. So for example, what we see in our everyday life is this, that is a floor tiles made up of squares. So this is a tiling. So each one is a square. So this is a regular convex polygon, and this is an H2H tiling. That means any two edges, any two consecutive or adjacent tiles meet completely along the edge. So we will consider these kind of tilings. So the question is, how many such tilings of the Euclidean plane can there be? So we are aiming to cover the whole Euclidean plane by means of certain regular convex polygons. So there are plenty of polygonal shape. For every integer n, you have a regular n-gon. So which of this actually can cover the Euclidean plane completely? So this is a simple question which has a very simple answer as well. So as we do in mathematics, we start with, suppose there exists a regular tiling with n-gons. So if I say, suppose there exists a regular tiling with squares, then we go back to the previous picture. This one. So this is a regular tiling with square tiles. So suppose I have used a regular n-gon. So now a regular n-gon. So what is an internal angle of a regular n-gon? So let us just refresh what you already know, that suppose I take a point in the interior and I join this point with all the vertices of the tiles. Now there are, if we have, this is a 6-gon, so there are 6 triangles. And if we sum these triangles, angles of these triangles, then this is pi. So if we add all the angles of these triangles, then this will be 6 times pi. But I would like to measure an internal angle. Okay. So I have to subtract this part. So what is the total angle around a point? This is 2 pi. And then because it's a regular polygon, all these angles are congruent. So if I divide this by 6, then I get the interior angle of a hexagon. Similarly, if I start with a regular n-gon, Then by the same formula, I have to replace 6 by n. So this is n times pi minus 2 times pi and divided by n. So this is the interior angle of an n-gon. So suppose in the particular tiling of the floor, m number of tiles meet at a vertex. So you look at the point where the tiles are meeting. So suppose this is one tile, this is another, this is another. So these are different tiles meeting at a point. So this number is m. I have already calculated an internal angle of the polygon that I have used. I have used only one type of polygon, that means an n-gon. So the interior angle is theta n, and if m number of such tiles meet at a point, then the total angle will be m times theta n. But we already know what is the total angle around a vertex. This is equal to 2 pi. So the equation says m times theta n must be equal to 2 pi. Already I know the expression for theta n. So if I substitute this value of theta n in this expression, I get the following equation. So this is a simple calculation. So if you have m times, this is n pi minus 2 pi divided by n, and this is 2 pi. So if you eliminate, if you just take out the pi from everywhere, you will see that you are left with this equation. This is a very simple equation. So what is the importance of n? So this is the n-gon that we have used, and m is the number of tiles that meet at a vertex. So what are the integers that their reciprocals add up to half? See, this have only finitely many solutions, and you can actually compute this by hand. So the solutions that you get is n is equal to 3, 4, 6. If n is equal to 3, then what is m? So suppose n is equal to 3 and this is half. So 1 over m is half minus 1/3. So this is 1 over 6, and then m is equal to 6. So this is one possible solution is 3 and this is 6. M is equal to 6, m, and n is equal to 3. So these are the possible solutions of this equation. Now let us see whether really we get a tiling using such a picture. So look at this. This is part of the plane covered by triangles. See, n-gon, 3-gon means it's a triangle. So I have used only triangles as a tile. And this is a vertex. How many triangles are there? 1, 2, 3, 4, 5, 6. Though exactly 6 many tiles are there. So this gives a one such tiling corresponding to the pair 6, 3. Similarly here, if I use 4, then this is 1 over n is 4. And if I take n is equal to 4, then 1 over 4 plus 1 over 4 add up to half. So this is the tiling that we get here. And this is just the dual tiling to this. This was 6, 3, and this is the 3, 6. So this pair has a name which is called the Schlafly symbol. So we have to remember this name. So you see that if you are considering only the regular tilings, then there are just 3 solutions. And the solution comes very easy. So now, as we do in mathematics, we try to make our life slightly more difficult and try to see whether that has a solution or not. So instead of considering one type of tiles, we shall now use more than one type of tiles to cover the floor. So this is called semi-regular tilings. So this uses more than one regular polygonal tile and they look the same at each vertex point. This means what? So this means that suppose in a semi-regular tiling, I have used M tiles meeting at a vertex. So suppose this is a vertex and so this is one picture. So if you look at this vertex, the picture is one triangle, one fourgon, that means square. This is a hexagon and this is again a square. So at each vertex, my picture is given by this is a 3-gon, then 4-gon, this is a 6-gon, and this is a 4-gon. So I'm looking for all such tilings for which at each vertex point, this sequence of numbers remain the same. So let us look at the next picture. So this is one such tiling. You take any vertex, you can see that you start with a triangle, then this is a square, then this is a hexagon, and then this is again a square in the anti-clockwise direction. Take any other point here. Again, you start with the triangle, then square, then a hexagon, and then again a square. So this is an example of a semi-regular tiling. And the vertex figure is given by this because you have used 3-gon, 4-gon, 6-gon, and 4-gon in this given order. So this is called the vertex figure. It has each vertex will have the same description. So this is the definition. So suppose in a semi-regular tiling, there are M tiles meeting at each vertex point. Further, the tiles are arranged in a sequential order, which are N1-gon, N2-gon, and Nm-gon. And this will be, this tuple of integers will be called the vertex figure. So again, I would like to see the following. So if you look at this vertex point, I know what is the internal angle of this. I also know what is the internal angle of this. This is a regular hexagon. I have already calculated the internal angle of a hexagon. And this is a square. I know what is the internal angle of a square. So if we sum all of this, that should add up to 2 pi. Because the total angle around the point is 2 pi. So this is what is written here. So here we have assumed that there are several tiles, N1, N2, and Nm-gon. And the internal angle for this I call is θ1, this is θ2, and this is θn. So as we have just observed, the sum of these angles must be equal to 2 pi. Now I just simply substitute what I have already got. I am substituting the value of the internal angle. So this is the internal angle of a regular convex Ni-gon. So if I sum it over, then I should get 2 pi. So I have just made a simplification here, and this reduces to the equation here. So as you can see, what are the numbers that appears in this equation? The number of tiles that I have used that meet at a vertex, and the nature of the tiles. That means N1, regular N1-gon, regular N2-gon, regular Nm-gons. So they are reciprocals, and sum of their reciprocals must add up to m by 2 minus 1. So this is an equation that we can deduce from a semi-regular tiling. Now, we also know that what is the minimum value of N1? To enclose certain area, we must have a triangular shape. That means the number of sides must be at least 3. So in this expression, in the left-hand side, each of these ni that I have used must be greater than equal to 3. So there are m tiles. So the left-hand side, if we look at the left-hand side, then this must be greater than equal to m by 3, because I have m tiles and each of this 1 over ni is less than equal to, sorry, this is less than equal to, because if ni is greater than equal to 3, then 1 over ni is less than equal to m by 3. On the other hand, if I look at this sum, I know that this is m by 2 minus 1. So m by 2 minus 1 must be less than equal to m by 3. And from here, if you solve this, you will see that m must be less than equal to 6. So number of tiles in a semi-regular tiling which meet at one vertex cannot be more than 6. Okay. So our solution set becoming smaller. So each ni have values greater than equal to 3 and m must be less than equal to 6. So what are all possible solutions of this equation? So I will just list all possible solutions. So suppose I have used 3 tiles. So n is equal to 3 means I have used 3 tiles at a vertex. So at one vertex, there are 3 tiles meeting the vertex. So in that case, the vertex figure, so this means what are the ni gons that I have used? So one possibility is there are, each of them is 3. This is 3 by 12, 12, 4, 8, 8, 4, 6. This is n1, n2, n3. That means this is 3 gun, 3 gun, 3 gun. Similarly, the other ones. Okay. So this is the all enumeration. So now, oh, I think I have made some mistake here. N is equal to 3. This would be 6. This would be 6 guns. Sorry. Because if you go back to the earlier 3 pictures, then you'll see this. Now, the green ones, you see, these we have already come across. This corresponds to the green ones. This corresponds to regular tilings. And this reds, there are no tilings corresponding, no semi-regular tilings corresponding to these numbers. That means there is no semi-regular tilings where at each vertex point you have 2 pentagons and 1 10 guns. There is no such tiling. Similarly for this. So we are left with 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9. This, and there were 3 before, which were 6, 6, 6, 4, 4, 4, 4, and 3, 3, 3, 3, 3, 3. So these are the new 8 tilings that we have classified. So you can see here, if we start here, this is a 3 gun, 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 and then this is a hexagon. So if we go to the previous thing, then this is what it corresponds to. So similarly, you can relate with these tuples the corresponding tilings. So there are 8 additional tilings if we consider semi-regular tilings. So these have a different, there's a name which they are also referred as Archimedian tilings. These were known for ages, and so as the name suggests. So what we have studied so far, we have studied what are the regular and what are the semi-regular polygons, semi-regular tilings. So in the regular tilings, I'm allowed to use only one type of convex polygons, regular convex polygons, and in the semi-regular tilings, we can use more than one type of regular convex polygons. So this is all about what we wanted to study. There are many questions related to this, but let us see something in a different setup. So here we were considering only the flat space, which is the Euclidean plane, and I was trying to cover this by certain type of tiles. Now suppose we go over to curved spaces. What is the most common curved space that we see around? This is in the shape of a globe. That means this is a sphere. So let's see this. What is a sphere? The sphere is a subset of R3. So suppose this is the X, this is Y, and this is Z. Then you have a sphere centered at this, and this, suppose this radius is 1. So these consist of all points which are at a distance 1 from the origin. And their equation is, in the Euclidean setup, this is x square plus y square plus z square is equal to 1. Okay. So we are all familiar with this. Now suppose you have a plane. And suppose this plane intersects the sphere. You try to visualize this. You have a ball, and suppose you cut this by means of a plane. What do you get? So the intersection, if you get a plane, so suppose the plane is x plus 2y plus 3z equal to 0. So just one representative. So if you intersect this with this and you solve, then this will represent a circle. So if this is the equation of the plane, and if you intersect with this, then it will represent a circle C, and its radius will be less than equal to 1. Of course, its radius cannot exceed the radius of the sphere. What happens if your plane passes through the origin? That means this is 0, the constant is 0. So it passes through the origin, then actually the radius of the circle that you get as an intersection of the plane and the sphere is of 1 radius. So the radius of C is 1 if and only if the plane passes through the origin. Such a circle is called a great circle because it has the maximum possible radius. So it is called a great circle. So why they are so important? Okay. So let us compare these circles on spheres with our straight lines on the plane. So there are many ways to characterize straight lines. So one such characterization is by this. So suppose there are 2 points in the plane. So you consider all possible curves. You consider all possible curves joining the 2 points and also consider the straight line segment. So you all know that the straight line segment has the shortest length. So you consider all possible curves joining x with y, and then you also have the straight line segment joining x and y. The straight line segment has the shortest length. So you can characterize the straight lines by means of this, that this is the, for any 2 points on the straight line segment intercepted between the points is the shortest path. So if you have the straight line, you take any 2 points here, and this line segment is the shortest path between the 2 points. So the great circle also has properties very similar to this. So first of all, let us look at a great circle here. So this is first of all a circle. Now if I choose 2 points, you can see 2 paths. So this is a point P, this is a point Q. So this is one path, and there is another path which is bigger one. Okay. So this is the smaller arc. This is the smaller arc joining P and Q. Now, if we consider all possible paths joining P and Q, such that these paths lie also on the sphere S2, then this great circle arc is the shortest path among all such paths. So this way, it is very similar to what the straight line is. So you know that on the sphere, there cannot be any circles. So I have to replace, there are no straight lines. So I have to replace straight lines by some curves, which could be thought of as an analog of straight lines on the curved surface, which is 2 sphere here. So for this reason, this is what we have written. Any 2 distinct points on S2 lie on a great circle. First of all, if you have 2 points on the surface of a sphere, then there is a unique great circle passing through this point. Okay, so let us draw this. So suppose you have 2 points here, and this is the North Pole, this is the South Pole. Then you can draw a great circle along this. So how do you get this circle? Suppose this is the center of the sphere. So there are 2 points which were given. So we got 3 points. This is the origin. This is the point P that was given. This is Q that was given. Now, given any 3 points, we know that there is a unique plane passing through that point. So that will be my capital P here. Okay. So let us denote it by small p, and this is by small q. So capital P will be the unique plane which passes through the 3 points O, P, and Q. Now, if you intersect capital P with this surface S2, then it is a great circle arc. So that great circle arc will contain this. So given any 2 distinct points on S2, there exists a great circle which connects them.
Mahuya, one quick question.
Yes.
This great circle between P and Q, any arbitrary points on the sphere, that
Yes.
may not pass through the North Pole and the South Pole, right?
No. Sorry. That may not pass through the North Pole and South Pole.
Yeah.
Yeah.
Okay.
So this may not be North Pole or South Pole, right? So what we do, I take the O, I take P, I take Q, I take the unique plane passing through these points, and then I intersect that capital P with the S2. That need not be the North Pole or South Pole, but some pair of antipodal points. Okay. So this is clear. Just like in the plane, if you have 2 points, you can always connect them by a straight line segments. Here, you can connect them by a great circle arc. And that is the shortest path joining the 2 points on the sphere. So the great circles are analogs of straight lines on S2. But you can see there is some difference, right? Great circles are some closed path, whereas if you look at the straight lines, it can be extended indefinitely. So we have generalized the notion of straight line by one of its characterizing property. So this is a different geometry, different from the Euclidean geometry. This is a geometry on a sphere called a spherical geometry. So what would be regular tilings? Now, in case of planes, what was our tiles? Our tiles were regular convex polygons. So first of all, what were polygons? Polygons were convex hull of certain points. But what was about the boundary? So given, say, 5 points on the plane, I considered the convex hull of these points. Basically, the boundary, if you look at, they are straight line segments, which were, in the case of sphere, that will be replaced by great circles. Okay. So what is a polygon on a sphere? So polygon on a sphere is a region bounded by great circle arcs. So let us look at this example. This is X, this is Y, and say this is Z. And this is the equator that you can see. And so if you look at S2 intersection XY plane, similarly, this is S2 intersection XY plane, S2 intersection XZ plane that I have not shown here. This will be this curve. And then S2 intersection YZ plane, which is the curve, the boundary. So if we look at, this region on the surface, which is bounded by 3 great circles. So this is a triangle or a polygon or a trigon on the sphere because it is bounded by 3 great circle arcs. Similarly, if it is a 5-gon, each of its side must be great circle arcs. So you can see that we are replacing straight line segments by great circle arcs on the sphere. So this is our new notion of tiles. So this is a trigon, regular trigon on a sphere. This is a very interesting feature of a spherical triangle. We know that in case of a triangle on plane, sum of all the 3 angles is equal to pi. This is a pi radian. What happens in the case of a spherical triangle, this is strictly bigger than pi and this is strictly less than 3 pi. So let us just accept this result. The proof is though easy, and I have given some references at the back of the this presentation. If you are interested, then you can go there and find the proof. So what happens in this case? So this is a very important feature of a spherical triangle. Spherical triangle means a triangle on the sphere. Because it's a triangle on the sphere, its sides are great circle arcs. So a polygon is regular if its sides are equal length and if the angles are congruent. This is the same definition. And what is the length of a side? It is the Euclidean length. So if there is a curve in R2, that means the sphere, then it is also a curve in R3. So I can measure the length of that arc. There are certain analysis formulas. So as before, a regular tiling of S2 is a covering of it by regular polygons, all of one type. So I'm allowed to use only one type of regular polygons. So the question is the same, and how many such tilings are there? So in contrast with the Euclidean plane, which was infinite, here we have a finite object. That means it's a bounded object. The plane was infinite, but sphere is a bounded object. So let us let T be a regular tiling of S2 with Schlafly symbol Mn. So recall what was a Schlafly symbol. It says if it is Mn, it means that at each vertex of the tiling, you have m many, these are m many tiles. Here it is showing 4 tiles. And what is n? It is saying that this is an n gun. Each of them is an n gun. Okay. So you are using n gun, and so each face is an n gun and each vertex is incident with m tiles. if you are say m tiles, so there are 4 tiles, 1, 2, 3, 4. At the same time, you can see that there are 4 edges which are incident on that. So again, as before, we will classify the regular tilings of 2 spheres by this pair. So remember what we did earlier, we found the interior angle of a regular polygon. And if you look at that formula, there we have used that the sum of the triangles, sum of the angles of a triangle is equal to 2 pi. That means if you have a triangle ABC, then angle A plus angle B plus angle C is equal to pi. This is what we had used. And using that, we got theta n is equal to pi by n times n minus 2. In this case, in the spherical triangle case, this is bigger than pi. So, as a consequence, you will see that the interior angle will be bigger than this. And again, as before, proceeding as before, if I eliminate, you will get that 1 over n plus 1 over m is greater than half. Because how did you get this equation? This was obtained m theta n, because m many tiles are meeting, and this is equal to 2 pi. So together with this equation and this inequality, I can get 1 over n plus 1 over n is greater than half. So again, I can solve for m and n, and the only solutions are only this 3, 3, 4, 4, 3, 3, 5, 5, 3. As you can see, this is just a flip of this number. So this is the case m is equal to 3, n is equal to 4, whereas this is m is equal to 4, n is equal to 3. Now I will show you the tilings for this. But we need to know something more. We will like to know something more. Because it's a this is a tiling of a bounded set, there cannot be more than finite number of tiles. So how many tiles one needs? In order to have a tiling whose Schläfli number 3, 3, what is the how many number of tiles we need? So for example, let us look at this picture of a sphere. So this is one such tiling, which I have already shown. So there are 3 great circles you can see. One is this one, one is this one, and the other is this one. Okay, so there are 3 great circles you can see. Now this is defining a tiling. How many such tiles are there? In the front you can see 1, 2, 3, 4. And in the back side, you can also get 1, 2, 3, 4. So there are 8 tiles which can cover the sphere. And each of the tiles is a regular trigon. That means a triangle, which is a spherical triangle. So this is one very simple example. And what is the MN value for this? If you look at this, there are 4 tiles meeting at this point. So this is the number. And what is the number of sides? This is 3. So this is 3. So this tiling corresponds to this 4, 3 pair. Okay. So let us go to the next slide. So I want to decide how many vertex, how many edges, and how many tiles I have used. So there is a name for the tiles. This comes from the mathematics language. We call them faces. So instead of tiles, we call them faces. And vertex we have already defined. Vertex is a point on the tiling where several edges meet. And edges we have defined, it's a part of the boundary of a tile, which is here a great circle arc. So given any tiling of S2, there are finitely many vertices, finitely many edges, and finitely many faces. So if you go to this previous diagram, here V is equal to, this is 1, 2, 3, 4, 5, 6. So there are V is equal to 6, because you have to count also top and bottom. E is 1, 2, 3, 4, 5, 6. This is 12. And face is 8. Okay. So in this particular thing, you have vertices. In the front, you can see clearly, but on the back side also, there is 1. So 1, 2, 3, 4, 5, 6. And edges is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Oh, age is also 8, sorry. No, and 12. It's okay. It's fine. 12. Because we have to include this ages. This one, this one, this one, and this one. Okay. So there are 12 ages. So basically, I want to find what are the values of VEF for the these numbers. For the 4, 3, I can see these many values. So how to find this? So here I will introduce a notion called Euler number of a tiling. This is the alternating sum of vertices, edges, and faces. So number of vertices, number of edges with a negative sign, plus number of faces with a plus sign. So this is called Euler number of the tiling. So I start with a finite tiling of S2 and compute this number. Now, this is a remarkable fact that whichever tiling you use, the Euler number of any tiling of the sphere is 2. This is a remarkable fact coming from topology. Of course, this means this is a branch of topology called algebraic topology, where you study all these things. So I will assume this theorem. It's not a very straightforward result, and you need a lot of machinery before you can come across this theorem. But it is truly remarkable. It says that whichever tiling you use, you compute this number, which is a combinatorial object. You compute this number, you always end up getting 2. Okay. So now there are certain relations between the number of vertices and number of edges. So you know that at each, what was the property? At each vertex point, there were n many tiles. That means there were n edges. So at each vertex, there are n edges incident to that vertex. There were v many vertex, so you have n times v edges, right? But you see, in this kind of counting, you have actually counted each edge twice, because any edge links 2 vertices. So when you have considered this vertex point, you have counted this one. When you have considered this vertex point, then again you have counted this one. So m times v is actually 2 times the number of edges. Similarly, suppose you have a face, that means a tile, and it has n edges because it's an n-gon. So it has n edges, and suppose there are f many tiles. So the total number of edges should be n times f. But again, here, every edge is common to 2 tiles. So you have counted this edge for this face as well as you have counted this for this age. So this number that you have got, n times f, that is actually twice the number of e. So these are the relations that you get between v, e, and f. On the other hand, you have the Euler number of the tiling, which is v minus e plus f is equal to 2. So here you substitute v and f in terms of e. So v is equal to 2e by m, and f is also 2e by n. So if you substitute it here, you will get the following relation. So if you substitute, so eliminating vf, you get 1 over n plus 1 over n is equal to 1 over 2 plus 1 over e. Now this right hand side is greater than half, which you already know, right? This we already got this relation, that if mn is the Schlafly number, then 1 over n plus 1 over m is strictly bigger than half. But now you can, this is now an equation. So from here, given the value of mn, you can read out the value of e, and then you can substitute the value of e here, the value of m here, to get the value of v. Similarly, you can substitute the value of e here, the value of n here, to get the value of capital F. So what are the numbers that you get? When the Schlafly pair is 3, 3, these numbers are 4, 6, 4, 3, 4, this is 8, 12, 6, and so on. You can see on the left, I have written down certain things which you may or may not be familiar with. For example, tetrahedron, I think many of you are familiar. There are 4 points. So 3 points, you can draw a triangle. And if there is a 4th point, which is not on this plane of the triangle, then you can join the convex hull. This is called the tetrahedron. So when your Schlafly number is 3, 3, then 4, 6, 4, this gives a tetrahedron. Similarly, Q, you can look at this picture. This is the Q. So at each vertex, how many faces are there? 1, 2, and 3. So this is the 3, and each rectangle, each square has 4 sides. This is 4. And then if you calculate VEF, you get 8, 12, 6. Now this cube has 8 vertex. It has 12 edges and exactly 6 faces. Now you might ask, we have started with, our question was related to regular tiling of a sphere, and we are drawing these pictures. What is the relation with this? Also octahedron. Octahedron is, the picture is like this. And similarly on the, so there are 2 tents which are meeting at a point. So you know the tents. Tent has 4 pegs. So this is the back one. So if you connect 2 tents along their base, you get the octahedron. So this is the octahedron. Okay. So what is the relation of this object? These are called regular polyhedrons. Just like regular polygons, these are called regular polyhedrons. These are in the 3-dimensional space. Now, because it is regular, suppose this is a square. Now, if you take the center of gravity, CG, from there, the distance of all the vertices are the same. So, from this center, if you take the radius, this, and draw a sphere, that will touch the cube in this 8 points. Now suppose you radially project each of these faces onto the surface of the sphere. Each such edge of this regular polyhedron will be projected on the sphere to give an edge of a tile. Each of this face, its projection on the sphere will give a tile, and so on. So basically you draw a sphere around the object which is called regular polyhedron around this, and from this center of this you radially project the whole figure onto the surface of the sphere. So that way you can get all the regular tilings of the sphere. So these are basically the pictures that are given of the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. So these are have a name also, Platonic solid. This regular polyhedron also have a name, Platonic solids. And each of this correspond to, so each of this correspond to a regular tiling of S2. So as I said, I will draw a sphere around this, and then from this point I will radially project this faces onto the surface of the sphere. I will get a regular tile. So may not be that picturesque here, but this is the way one gets. So let us summarize what we did. We started with regular tiling of plane by convex regular tiles. Then I generalized the concept of tiling, regular tiling, to spheres. And in classifying all these tilings, what I have used is the fact that the sum of the angles of a regular polygon, sum of the angles of a triangle is somehow related to pi or strictly bigger than pi. So in case of Euclidean geometry, we have 1 over n plus 1 over m. This is half. In the case of spherical geometry, we have 1 over n plus 1 over m strictly bigger than half. So the question is there any geometry for which 1 over n plus 1 over m less than half? That means, is there any space where you have a regular tiling with roughly number mn which are related by this always? This is the question. This is equivalent to saying, can we have a geometry in which the sum of angles of a triangle is strictly less than pi? Remember, this is exactly what we used in the first two classifications. Here, the sum of the angles was equal to 2 pi in the first case. Here, it was bigger than pi. And so the question is whether there are some geometry where the sum of the angles of a triangle is strictly less than pi. So this is a model. This is called the Poincare disk model for hyperbolic space. This is slightly more advanced. So here the space is the open unit disk in R2. So in the plane, you have the open unit disk. So the boundary is not included. So norm of x less than 1. So x is a point in the plane. That means if I say x1 square plus x2 square is less than 1. But the metric means the notion of distance is not the Euclidean metric. So you remember how we, in the plane, what is the distance between 2 points? I draw the straight line, and the length of the straight line, that is the distance between the 2 points. That's the Euclidean geometry. Okay. And in case of the spherical geometry, I have 2 points. I draw them by I join them by a red circle arc and look at the length of this arc, that is the distance. Now what happens in this? This is subset of R2, but the notion of distance is different. So take 2 points, again in the disk. Okay, so this is a curve. So curve means this is a function from an interval to the disk. So because it has 2 coordinates, I can write it as x coordinate, y coordinate. Okay. The length of gamma is given by this formula. This is an integral of some function between t0 and t1. Now look at this very carefully. If there were no denominator, only the numerator, then that gives the Euclidean metric. That means if we simply integrate between x prime t square plus y prime t square and take the root over and integrate it with respect to t, that gives the Euclidean distance between 2 points, which are gamma t0 and gamma t1. So this will give the Euclidean distance. But I'm using the same space, but I'm using a different way to measure. So there is a weight function in the bottom. So that will give the measurement. Now, if I measure this, then I can ask what else? Suppose I give 2 points on the disk. What is the shortest path between this? Shortest path with respect to this measurement. Okay. Then what happens is the following. So the lines that I call line, which have this property. So the lines in this geometry are arcs of circles which intersect the boundary of D orthogonally. That means if you have a disk, what are the lines? Suppose I consider sphere. These are the part of circles. The other half is outside. So these things are considered lines. Why they are called lines? Because lines within inverted comma. So if we take 2 points, then the path, this arc has the shortest length among all paths joining the points, joining these 2 points, this small p and small p. That is why it has the property of a straight line, that if you choose any 2 points on that line, then the straight lines, the segment which is intercepted between the 2 points has the shortest length. So this is the lines in the new space. And again, one can show that given any 2 points, you can get such a circular arc which intersects the boundary orthogonally and passes through this point. So this metric is known as Poincare metric on the real. And for this metric, if you take a, say, triangle, so its triangle will be, as you can expect. So these are some of the, that's not a good picture. So some of the angles, 3 angles, this would be strictly less than pi. This is one line, this is another line, and this is the third line. So this is some picture of a regular tiling on the Poincare disk. Okay, so each of the tile is a trigon, and at each vertex there are 1, 2, 3, 4, 5, 6, 7 things meeting at a vertex. So we can see that the tiling problem is associated to 3 types of geometry. It started very combinatorially, but finally you can relate it with the geometry of the surface that you want to cover. Okay, I think I'll stop here now.
Thank you. Thank you, Professor Mahuya. So,
yeah, thank you very much, Mahuya, for this beautiful talk. And now you can take some questions.
Sure.
Okay.
okay. So, Rukmini, I'll read out the questions.
Sure, sure.
Okay. So, Professor Mahuya, we have the first question from Kshitij. And I think he was referring to slide number 35 or 36. There is a equation he is referring to.
Which, okay,
I'll read out the question first.
Yeah.
Why is n, small n, greater than or equal to 3 on a sphere? There can exist a 2 gon as well. Right, he's asking. So.
Okay. No, we will always consider minimum 3 gon. Yeah. Though,
Okay.
of course, you can enclose certain area using 2 red circle arcs, but we will start from 3 gons.
Okay. And the next
and
question.
If you actually allow, say, like these 2 gons, then as you can expect that there are infinitely many such tilings. You can divide the 2 pi angle into any integer, and for each such 2 pi by n, there is a slice, basically. So if you have this sphere, this, and then, so you can have this slice. That is what he's trying to say, I think. So no, we'll not consider such things. These are degenerate triangles. So we'll consider at least 3 onwards.
Okay. Thank you, Professor Mahuya. And okay, just a minute. And the next question is by Soumyadeep. He asked why the Poincare disk needs to be closed. Why the Poincare disk needs to be open. That's the question.
Yeah. So you can see here, though this looks like a finite disk, actually the distance between the points which are closer to the boundary is okay. Let me go to the previous. See here in this. This is one of the models, by the way. There are various models of the Poincare the hyperbolic space. So this one you can write 1 minus norm of xy whole square. So as the point approaches to the boundary, this denominator blows up. Sorry, this goes to 0. So the distance becomes actually infinite. So this is a very, this gives you a finite feeling, but the points which are closer to the boundary, first of all, this will not exist, as you can see. If norm of xy square is equal to 1, that means if we include the boundary, this integral does not exist. And what is the consequence of having such a thing? It says that the points which are closer to the boundary, means suppose I take a point, its distance from the boundary is infinite. Though it looks, in terms of the Euclidean distance, it is at a finite distance. This is a finite distance. But if you use this formula, then this goes to infinity. Because 1 minus norm xy square, norm xy square goes to 1, so denominator goes to 0. That means the whole thing integrand is very, very large. So as the points, so there's a sense of infinite distance is hidden inside the metric. I don't know whether this is exactly the answer of yours, but I cannot, because of this, I cannot, at least this is clear that because I have this in the denominator, this is the reason I cannot include the boundary. But there are other models for hyperbolic spaces, for example, upper half space model, which equally common to see. But this is very important, interesting feature actually. that points towards the boundary, its distance, this is very, very large distance. It's not bounded by 1 at all.
Thank you. Thank you, Professor Moore. These were the questions so far we have received.
I had one question. Yeah, no, Anupam, go ahead.
Okay, I had a very general question. So basically, the tiling is allowing us to figure out new geometry. Is that right?
No, I want to say that means you define tiling based on the space. Means you have to generalize the notion of straight lines in other spaces. So geometry is controlling the tiling.
Okay. Okay.
So
Thank you.
yeah. So what I wanted to ask was, supposing you have a genus G surface, the genus is greater than 1. Universal cover is the Poincare disk.
Yeah.
So can you talk about tilings which actually drop down to the genus G greater than 1 surface? And
yeah, I do not have any, but there are some trivial examples of tilings, but how they are related, I don't see them.
Okay.
Yeah, I don't see them often. Yeah.
Okay. Okay. All right. Thank you. So if there are no other questions, let's thank Mahuya again for the wonderful talk. Very beautifully presented. Thank you so much.